So we are reaching a limit of lack of preparation that really starts to be borderline with actual new science on the fly. So today we are going to start by looking at how we can compute piezoelectric response from the simple model that we introduced the last day, in which we growth free energy, Landau free energy for both polarization and strain. Okay? So just as a quick reminder, we argued that we can write in the simplest of ways a Landau potential that looks like this. P to the fourth. Then for the strain, we have a purely elastic part that looks like that. And then we had the lowest order, the simplest possible coupling between strain and polarization that we saw goes like a strain linear in strain and quadratic in the polarization, and for which we use a letter, I think it was gamma. Now we are going to use B, which is a more standard notation for that one. Okay. Here, all the parameters are positive, and we have discussed repeatedly. And B, we argued that B should capture a piece of physics, which is that when you elongate the cell along the direction of the polarization, it should make it easier for the polarization to appear. That means that when eta is positive and P is different from 0, the energy has to go down according to this coupling. Okay, and for that to happen, we need B to be negative. Okay, so this is our basic model of a ferroelectric with a continuous phase transition at Tc, and including explicitly the coupling with the strain. All right. Now, the other day we ran an exercise in which we said, okay, let's imagine we can control the strain from the outside, and we use the strain as a parameter. That, of course, is fine, and it's very similar to what you need to do when you grow a thin film and you fix the epitaxial strain to that of the substrate. But now here we are going to use the strain not as a parameter, but as a variable. Okay, so it is on the left-hand side of this semicolon. And so, if it is a variable, it means that when we think about the equilibrium state of the system, the equilibrium state has to be a minimum not only for the polarization, but also for the strain. Okay? And instead of having a single equation of a state, we are going to have two equations of a state. Simple enough to write them down. So essentially, exactly as before. Oh, by the way, here, let me put a term that shows the coupling between polarization and electric field. We could add trivially a term that couples the strain to the external stress, but in this lecture we are only going to operate with an external electric field. In fact, let me just to state where we are going towards. When I say we want to investigate the piezoelectric response, specifically, I mean that we want to investigate the following piezoelectric coefficient. Typically, we call D, and which will tell us how the polarization, how the strain changes when I change the electric field. Okay, that derivative is the one that we are going to try to evaluate. So obviously, it's a cross coupling between elastic properties and electric properties. There are other piezoelectric coefficients, but those you can learn about in textbooks. We don't have to worry here. If you know how to do this one, pretty much you know how to do any of them. All right, so obviously the strain has to be treated as a variable in order to evaluate this. It cannot be an externally imposed parameter. And so we have to minimize this free energy with respect to both polarization and strain for given values of temperature and electric field, which we are going to vary. Okay? So the first equation of a state is as before. df dp at equilibrium has to be 0, and this gives us an expression that is very similar to the one we are used to, but which now contains some extra terms that come from the coupling between polarization and strain, right? So essentially here I have an extra term coming from there, 2 times eta p, and this is equal to the electric field. Okay, so we used to have this, but now the strain affects the energetics of the polarization. Fair enough, it wouldn't be fun otherwise. And the second equation of state comes from demanding that the first derivative of the free energy with respect to the strain at equilibrium has to be zero as well. And this one is very, very simple. We have from the purely elastic part of the free energy, we have a term like that. And then from the coupling to the polarization, we have a term like this. And eventually, on the other hand of the equation, we would have here something like the stress. Okay? But for the moment, we are going to imagine that that one is zero. Okay, so two equations of state. So now only with that, you already see that nothing can be exactly as before, because if the strain is different from zero at the minimum, then this equation, the energetics of the polarization, will be modified. So nothing can be as before. Nevertheless, we can kind of try to proceed almost as we did before, right? Because since the part of the strain is so simple, which ultimately has to do with the fact that the strain by itself cannot do anything, as we emphasized the other day, if the polarization is zero, the strain lives in the minimum of a potential. And indeed, if the polarization is zero, that would be telling us that C times eta equals to zero, which means that eta is zero. So the only reason why the strain is different from zero is that we have a polarization in this very simple theory, right? So that, in fact, this equation gives us immediately a relationship for the strain, because the strain, again, this is zero, is simply B over C multiplied P squared. And this is true always at equilibrium. Always true at equilibrium. All right? But if this is always true at equilibrium, this in effect means that I can always write, for the equilibrium solutions of these two equations, I can always write the strain as a function of the polarization. Always, without any doubt. And therefore, let's do that. So I can use this to rewrite the equation of state for the polarization, which then would look the following way. I have the usual only polarization part, cube. And here I have a term that depends on both the strain and polarization, but I can always write the strain as a function of the polarization, right? So let me do that. So I have here a minus 2 times B squared over C P to the third. Any mistake? I don't think so. And this whole thing is equal to the electric. Reasonable? Okay. And now this equation is asking us to kind of reorder terms a little bit. So let me do the following. Instead of this, let me write alpha prime t minus t c p. But then I have two terms that go as p to the third power, right? So I can put them together and write something like this: beta minus 2 times b squared c multiplying p to the third. This is the electric field. So formally, the equation of state for my system in which the strain can relax to help accommodate polarization is exactly the one I had before without the strain, but with the difference that this term, this coefficient, is not beta, it's beta minus 1. So let me call this guy actually beta tilde, and say that simply my equation of state of my system with a strain is this. Beta tilde p to the cube equals to the left. Okay, so what have we done here? And this can generally be done as long as the energetics is not too complicated. Well, as long as if the energetics is not too complicated, it can even be done analytically, let's say. When we have a secondary variable like the strain here, which is a slave to the polarization, is very important for the physics, but ultimately it will always adopt at equilibrium a value that is dictated by the polarization. When we have such a situation, we can essentially get rid of the variable in our theory, okay, by simply writing it, expressing it in terms of the primary order. When we do that, typically we end up with expressions that look, by symmetry, they have to look essentially the same as before, but where some parameters have changed. Okay, and this new parameter, this beta tilde in this case, is what we call in this case a strain-renormalized parameter. Okay, so this beta tilde captures implicitly the effect of having a strain that can relax to further lower the energy when we have a certain polarization and we are at equilibrium. So to all practical effects, if we are all interested in equilibrium solutions, we could in fact we could work with a theory that all that doesn't contain strain explicitly. Let me just make room and write it at least once to show it. Let me write it here. Noticing this, we could write the Landau free energy for this system and taking into account strain as follows. We could write an F tilde of polarization and temperature, where the tilde means that the strain is somehow taken into account, that is like this, P squared okay, which is exactly identical to the one that we used to have, but where the beta parameter has changed. Okay, and the new beta parameter, which I have thoughtlessly removed, looks like 2 times b squared over c, I believe. So beta tilde is beta minus 2 times b squared over c. Is that correct? Is that what I wrote before? Okay. Okay. A few comments here. If we compare beta tilde to beta, actually they are related in a very specific way. Because this number here, b is a negative number, but we have b squared, so it's positive, c is positive, number 2 is positive, so beta tilde is always smaller than beta. Okay? So if we compare the energy wells, let me make room here. If we place out our cells at a given temperature below Tc and plot the energy well corresponding to F. F meaning F. The energy well given by alpha prime T minus Tc P squared plus beta without renormalization P to the fourth, okay? So the energy well that would correspond to having all the polarization without the strain, have something like this. And if I plot now the energy well corresponding to F tilde, which is the renormalized version, Maybe green is a better color for that. So at the harmonic level, it will be exactly the same. But then beta tilde is smaller than beta. So actually, at some point, when we go up, we will go up a bit later. So systematically, if we allow, but this is very natural, right? We have an extra variable, and by relaxing this extra variable for any value of the polarization, all that we can ever do is to reduce the energy. Okay? We have increased the variational freedom of the problem, if you wish, and this extra strain that can be optimized, if it will do something, it will be to reduce the energy. It cannot increase the energy. For increasing the energy, it would take the value of 0, and that will be it. So systematically, this green curve is lower in energy than the black one. Okay? This will happen with strain here as a secondary order, but with any secondary order that you can imagine. This has to be general. What else do we see from these general formulas? Another thing that we see, which is quite nice, and that makes sense with the physics that we discussed the other day, is that the strain doesn't depend on the sign of the polarization. So if you remember, the other day we discussed, we gave a physical argument as to why when I have a positive strain like this, okay, I strain my little square unit cell that we are always using, I stretch it, I will increase the tendency of the polarization to go out, right? Likewise, in a way that doesn't distinguish between going up or down. Both polar states will be satisfied, or will be favored by strain. Conversely, if I create a polarization, be it up or down, I expect the strain to be expansive. Okay, that's what reduces the energy. And that's what we are exactly getting. The sign of the polarization doesn't matter, that's good. And this number, minus b is a negative number, c is positive, so this strain is always positive. So whenever we have polarization, strain grows, becomes positive. Okay? A very general observation in ferroelectrics that is ultimately rooted in this piece of physics, and which we obtain here in a different mathematical. Okay? All those things come about quite naturally when we do this simple theory. Just pushing, just examining the equilibrium solutions, we recover a lot of physics that we were essentially hypothesizing before. And it's contained in this very simple coupling term.